Good morning, everybody. Right, my name is Won-Jae. I'm from EC Department of Illinois Institute of Technology in Chicago, Illinois, and I'll be presenting to you my work on wireless sensor network for structural health monitoring using system on a chip with Android smartphone. And it's co-authored with my other colleagues, Dr. Gilliland, and my advisor, Dr. Jafar at Embedded Computing and Signal Processing Laboratory. So as for the motivation, as far as the non-destructive evaluation goes, there are plenty of options that we can think of. Like, for example, like well verification, structural mechanics, or we can even use for medical imaging, and also all sorts of different types, such as like ultrasonic added currents, radiography, acoustic emissions, and so on. We got like a lot of options to explore from. But in this particular paper, we kind of wanted to explore where we can utilize more data mobility to the NDE and the civil structures. So as far as the civil structure goes, we need constant and periodic measurements for inspection to get the, like aircrafts, building stands, and all sorts of structures that we can see out in the environment to maintain its, safety and so on. And then why not we implement some kind of a mobile system into this so that we can monitor the status of the structure in real time in a remote location. So one of the examples of the NDE, we can utilize ultrasonic data. So basically, as many of you know, that for ultrasonic non-destructive evaluation, we just look into the two dominant echoes that can be found when it's entering the material and exiting the material, and then for the possible flows that can be found in that particular material, we can possibly detect that kind of a flaw based on the ultrasonic data. But the problem with this is that since this arrangement is down on the water, so in this result we don't see that much of a scattering noise, but in the real environment we're going to be seeing a lot of noise in between these two dominant echoes. And this is our previous work, actually it's ongoing work in our research laboratory, that we call this particular platform as Reconfigurable ultrasonic system on a chip hardware, aka RUSH. So we have this FPGA system that can do real-time ultrasonic signal analysis and image processing with the range of 20 kilohertz to 20 megahertz. And previously we were working on, I believe, two different FPGAs, including 364 and 365. And then now we are in the transition of upgrading to the new Xilinx FPGA with the external ADC board, and then since this has an Encore chip in it, so that we can utilize some embedded Linux application on it, and we can use put pre-fills into the FPGA more easily. So the reason why I have put the Bluetooth transceiver on this FPGA is that I wanted to utilize smartphone as like a display equipment when we are doing like structural health monitoring on it. So like all this data that collected on the FPGA for the ultrasonic data, and then it does all the signal processing that it needs to detect the flaws, and then we can use our smartphones that we all have in our pockets to display what kind of data it was, and then what kind of data it was, and then see the results of the structure or some kind of data that you were expecting to see. So I just named this whole system as MSDC Mobile Sensor Data Collector, which was previously my other research work, which was based on the wireless body sensor network. And the thing about our smartphone is that we got a variety of wireless protocols that we can utilize. for example, Bluetooth, Wi-Fi, and then if we don't have Wi-Fi, we can use our cellular data network to connect to the internet, and then, of course, and then we get the NFC. The biggest advantage of using a smartphone is that it's user-friendly, and the battery life is kind of horrible. So, and then right now in the contemporary smartphones, we got like 4 cores embedded inside, so it has like proper processor with adequate RAM space. Right now, we got like about 2 gigs of RAM, so we can utilize this kind of embedded system to be a really powerful device to do more signal analysis. But in this particular paper, we only use this as a gateway to connect to a central server location so that we can use internet connection, and then we share that out all the analyzed data on the Rush platform, which is the FPGA I just told you before. And then on that server side, we can do extensive more data analysis, and that PC will have more what I call it, the processing capability. So in our study, as far as this conference goes, we're introducing a design floor of consisting environment sensors, smartphone, and the FPGA, which does data collection of the sensor data, is not restricted to ultrasonic data, and signal processing and data transmissions, where we can transfer data from one end to the other end using multiple wireless protocols. So in this case, I'm using Bluetooth connection between the FPGA to the smartphone, and then smartphone to the central server using the internet connection. And then here I got the server that's just for preliminary approach to display the data and then store the process data on the server. So that's like the more brief diagram of our design. So here the Rush is the FPGA where it actually collects the environment sensors and like the ultrasonic network right here. And then all the data goes to the MSDC, which is the smartphone, and then it displays everything and then shoots it out simultaneously to the sensor. So this architecture is actually is like an extensive approach from my preliminary wireless body sensor network, where this Rush and those sensors can be directly transported to the smartphone, and then smartphone has powerful processors, enough processing capability. So on this plan, you can do more extensive signal processing with like accelerometer or vibration or temperature sensors and so on. And this is one of the examples that can be applied when it comes to flaw detection or say structure. So for ultrasonic data, we use this kind of application for our Rush system. It's called split spectrum processing. So as all of you might have known that the SSP is kind of an algorithm that able to detect the flaws within the structure, where it uses simply FFT and then inverse FFT, and then it does it divides into subbands as desired. Like in this case, we use 4 subbands, but it's capable of doing like 8 subbands or 16 for more extensive flaw detections. But in this case, we use only 4 channels. And then after the SSP algorithm running, then we have the post-processing block where it reduces all the scattering noise energy to the minimum, and then choose the minimum sample within the output. So this is like the output of the SSP algorithm of the ultrasonic data. So as you can see, we got like 1, 2, 3, 4 sub-channels, and then those like are the scattering noises, but you can see the float right there is kind of dominant. And then in the output, it's going to run that post-processing algorithm, and then it will detect a flaw. And this captured data is actually a screenshot of my phone. So the collected data gets instantaneously displayed on the phone, and then simultaneously all those data points that is used for these graphs gets sent to the server for further data analysis and so on. So on the rush, it takes about like approximately 0.1 second to run a 2048 data sample, which gives us like 10 measured signal can be processed with the combination of the both FPGA and the smartphone, and which is highly practical for routine structural health monitoring. And then I said before, the data transfer is like kind of seamless and real time between the FPGA and the smartphone and to the central server using Bluetooth and the internet. And for structural health monitoring, not only ultrasonic data can be used for detecting the flaws, but we can combine all sorts of different sensor data, such as accelerometer. This is one of the examples that showing that accelerometer can be selected and then shoot it out to the server instantaneously on the smartphone and so on. And then I just put like the Bluetooth magnetic just to see that which accelerometer data I'm actually getting it. Same thing goes with the temperature sensor. This can be used for like surrounding temperatures within the building or and so on. This time is the same thing using the Bluetooth connection that shoots out to the phone, and then it draws that graph on the phone screen in real time, and then it gives the valuable information to the sensor server with the timestamp and the current temperature. So to sum up, this study is kind of a system architecture floor of the wireless sensor network system for structural health monitoring, but this is one of the other approach to the wireless body sensor network, where all sorts of wearable sensors that can be integrated into one node or can be connected into one node, and then that node could be send the data to the phone, where the phone could do more processing on it, and then it gives you more user-friendly display of the data that has been collected on the phone side, and then simultaneously shoots out to the central server for remote monitoring. So in this case, it can be used for structural health monitoring in real time, but if it's applied to the wireless body sensor network, it will be more extensive way to approach for remote patient monitoring. By utilizing this kind of system architecture floor, I think it will give more data mobility to the analyzing and monitoring of the critical structure. So, okay. Thank you for your attention.